All right, so we begin a new program of joint lectures with the physics department, and our inaugural speaker is Nikita Nekrasov from the Simon Center, who's going to tell us about Lefschetz thimbles and quantum theory. Nikita?
Thank you very much. So it's a great honor to speak on this topic at the conference related to the legacy of Solomon Lefschetz. And so when you invited me, I felt obliged to say something about the role of Lefschetz in modern physics. And so this is the topic I came up with. Now, Nick also told me that the conference is called Lefschetz Centennial. And so I was thinking, without knowing what Ernesto was going to talk about yesterday, about what really happened in the life of Lefschetz 100 years ago. And so one thing which happened on the earthly level is that he got a job, and on a more important level, he reached for a theory, so, which we now call the correlation theory. So Carl, of course, worked complex. This is multiple functions. Right. So this is I'm getting there. So Picard worked on complex functions, analytic functions 50 years earlier, but Lefschetz grasped the picture. And now, as I said yesterday, my life somehow is intertwined with the two Lefschetz per se is intertwined with life of Lefschetz. But at any rate, we really shared some paths, and by some miraculous accident, in my early days of studies, I was taught singularity theory, and so this is one of the first pages of the second volume of the book on singularity theory, the book of singularities of differentiable maps by Arnold, Marchenko, and Bethe. And so that's we don't have to understand what's written there, but you understand the pictures. So this is you see the vanishing cycle. Oh, no pointer. Is there a pointer? So you see the vanishing cycle, and then you see the cycle which intersects transversely, and then you see the monodromy and the radiation map. And so that's probably that's as much Lefschetz theory we'll be using, but that's actually a lot. So this is where I took it from. So I took it from my book, which was written in Russian. This is the English translation. And so one concept which came out of singularity theory, or came out of Lefschetz theory, and got absorbed in the branch of the singularity theory, which deals with the projects of exponential or oscillator integrals, is the notion of Lefschetz thimble. I actually don't know who came up with this name, and I suspect that it was a person who was probably too impressed with the Lefschetz character, because naming something. So Lefschetz, of course, is famous for having things named after him. So he has a number. Lots of people have numbers named after them, but to have an SU2 named after Lefschetz, that's I think that's the only one. So there's only one Lefschetz SU2, and so there are these Lefschetz thimbles, which is, of course, you understand that thimble has a shape, and the shape sort of represents maybe Gaussian or some kind of a counter of steepest descent, which it actually is. But to call it Lefschetz thimble, I think it's kind of a bad joke. Because Lefschetz no hands, but so he could not. In Russia, where Lefschetz came from, at the time when he came from, so there were many anti-Semitic jokes. So one of these jokes was that some old Jew is talking to another old Jew, and one asks now, what would you do if you were a king? I understand that, well, I would live much better than the king, because not only I would be a king, but I could also have time to sew on the side, so to do a little bit of tailoring. And so that's what, in mental image, what do the Jews do? So they have some business, but they also do some tailoring on the side. So to do tailoring, of course, you need thimbles, because otherwise you pick your fingers. So anyway, so this is typical. So the general idea is by now very well known, and it's probably in the point it's part of the light map. It's not really you want to evaluate an integral with which has some regular measure, which I will assume to be analytic top one, some real equal. Imagine n, and which you multiply by an exponential of the regular function, and there is a small parameter. And so if everything is analytic, the integral doesn't change when you deform the contour, and so you can deform the contour in the contour's domain, and maybe you can choose a better contour so that you can find some approximation scheme to make the integral converge faster and evaluate it with better precision. And so this is what it is. So you try that you can complexify the space over which we integrate. So the original space will become a middle dimensional real slice in that complex manifold. And then you can automate the process of finding the better contour. And this is what reinforced learning does by deforming the contour in a certain direction. And so the way you do it is to you pick your favorite emission metric of the space and just make a flow along the gradient computed with respect to this emission metric of the real part of the thinking in exponential. IS of H bar is the whole exponential. So now if I flow along this vector field, the real part of IS of H bar decreases. And so my exponential decreases a bit faster, and so the integrand becomes smaller and smaller. So I'm flowing the contour in the direction where I have less to integrate. But of course, the whole integral doesn't change, so I'm just doing a better job of testing. And but now so you can flow and flow until you get stuck. So where do you get stuck? Well, you get stuck at the zeros of this gradient vector field. And because of the analyticity of the function S, so I imagine I do analytic continuation, so it becomes a holomorphic function of my complexified space FC. I will get stuck at the critical points of this function itself. So if you analytic function and the gradient of the real part vanishes, then the gradient of the imaginary part also vanishes. So the whole gradient vanishes. And so you will get, so your original contour, well, it gets pushed into different directions maybe, and different parts of the original contour will be approximated by the limiting cycles, which will be attached to the different critical points of your function S in the contour's domain. And now, so if you follow this process back, to each critical point, you will assign a cycle, which will be the union of trajectories, gradient trajectories, which emanate from this point. And then the original contour, original cycle. So those cycles will form a basis in the relative homology group. So this is the middle dimensional homology of the complexified space modular the region where the real part of the exponential is segregated. So the space is not compact, but I'm taking the relative homology, so it's almost like compact. The useful fact is that the imaginary part of this exponential is actually constant along this flows. So you can distinguish different cycles by looking at the images of the imaginary part of the function values of that.
Recording in progress.
And you can also define the dual thimbles, so dual cycles, which obtained by taking the union of trajectories which enter the critical point. I think Moore's theory came after this, but this is, of course, these are examples of more cells or critical point of a function which has an index equal to the half of the dimension of the. And so the original contour, the original cycle we were supposed to integrate, will be a kind of a linear combination in homology, in this relative homology, will be a linear combination of the cycles assigned to critical points, equal combination of Lefschetz thimbles, and the multiplicities, these numbers and A, are computed by taking the intersection of this original cycle with two Lefschetz thimbles. Details are not very important. What's important, of course, is that I told you a complete lie, but not a complete lie, but I somewhat lied. As I learned yesterday, this is the spirit of Lefschetz approach. So things are a little bit more tricky because sometimes often critical points are not isolated. And so you need to do a little bit more work. The critical point is not isolated, we'll discuss it. So if it is isolated, then. And so this is a little bit of cartoon. So there was this original cycle, which was purple. And then I made this transport, deformed it into pieces. And then, so this example, there are two critical points, 1 and 2, and they sit somewhere in the complex domain. So you don't see them if you live on the real line. So the idea, which some of us had for many years in the dream, is to apply this to path integrals. So in physics, we want to make sense of an infinite dimensional generalization of these exponential integrals. And we've learned over the last 50 years that these integrals, when they are defined, in some sense, they exhibit very intricate analytic properties. They have very interesting dependence on the parameters. One example is the famous Dyson argument for non-analyticity, or say the zero. Actually, the Dyson argument is for the zero radius of convergence of the perturbation series in quantum electrodynamics, so zero electrons and photons. Feynman, who will be mentioned later, introduced a scheme of computing radiative corrections to various processes involving charged matter and radiation. And these calculations give you an answer as a power series in a small parameter. The parameter of the finite structure constant, which is the square of the electric charge, the probabilities, which is at our energies is equal to 1 over 137. So it's a small number. So you have a power series in a small number, and you compute correction after correction. These are kind of small corrections until they aren't. And so Dyson made an argument that if you had a conversion series, would have continued to the region when the square of the electric charge was negative, but that would, in that case, electrons would start attracting each other, and so there would be complete collapse of charged matter, and the universe would be completely different from what we see. So something has to happen which prevents these power areas from converging. And the other way of saying this is that there are non-perturbative effects, and non-perturbative effects have to do with the fact that this exponential integral we're trying to make sense of receives contributions from many standard points, which most of them sit in the complex. Now, in high-GP's community, we interchangeably call the path integrals also Feynman integrals, because Feynman was essentially one who understood that the old-fashioned quantum mechanics and quantum field theory, which was being created at the time when he understood it, could be formulated as if an integral over the space of paths and more generally over the space of fields was a meaningful concept. So classical physics, which usually follows a variational principle, for example, Euler-Lagrange equations are the equations which can be expressed as the extremum of some functional. So this would be the result of the stationary phase approximation to that integral, but the integral is different from the stationary phase approximation, hence there are quantum effects. Now, when I was preparing this talk, I came across the book which Lefschetz wrote not 100 years ago, but 50 years ago, which he used the knowledge that he used the theory which he came up with 100 years ago to apply it to very simplistic problems 50 years later, towards the end of his life. So he wrote a book which is called Applications of Algebraic Topology, innocent title. But if you look at the second page, you see that he talks about graphs, networks, and final integrals. And so when I found that, I was not really scared. I thought, what am I going to talk about if he already wrote a book about 50 years ago? Well, it turns out after certain inspection of what he actually wrote about was that, so this is an English book. He was talking about different kind of final integrals, the ones which you study when you take one particular stationary point of contributing to the exponential integral, and then do the asymptotic power series expansion with small parameter h bar. So this, you got this contributions which are labeled by graphs, various graphs, they're called Feynman graphs, and the contributions of the given Feynman graph is also called the Feynman integral. This is a finite dimensional integral over some configuration space or momentum space itself. It's an integral over innocent looking algebraic differential forms. So he was studying those integrals and applying Lefschetz theory. It's still a very active domain of research. So this is what people compute in when they do their loop calculations, when we think about them. So these are the effects of virtual particles. And this is where quantum field theory defends its title as the most precise theoretical science. Because for certain processes which involve behavior of magnetic moment of an electron, these calculations has been done to extreme, many orders in perturbation theory, and they give you predictions which are verified in 12 or 13 digit. It requires also very high precision experimental techniques, but also highly sophisticated techniques of computing those integrals. So today we're not going to talk about those integrals. I want to explore the structure of path integrals themselves, of the whole exponential integral viewed as periods. And to start off, I want to start with something relatively simple. It's a quantum field theory in 0 + 1 dimension, so we have all space and time, which is also known as quantum mechanics. So in quantum mechanics, we're interested in computing the spectrum of an operator, H hat, a Commission operator, operating in the Hilbert space, period H. So the real life evolution quantum mechanics is represented by a unitary operator. So unitary operator can deal with an exponential of I times time times this Commission operator. But unitary operators have nicely traces. So if I want to compute the trace of the unitary operator, most likely I will get some distribution which is hard to deal with. So the typical trick which is done is to do what's called the weak rotation, where you replace the imaginary coefficient of the Hamiltonian by the real one. So make time imaginary, also it's called inverse temperature. And instead of the unitary operator, you get now a compressing operator. Compressing, assuming, of course, that this operator H hat, which is called Hamiltonian, has spectrum bounded below. So that guy may and often has a nice trace, and this trace gives you the information about the added values of the operator. So this is what we want to evaluate. What I see. And so according to Feynman, you can represent it, well, this is really due to Fazit. So Feynman was thinking about the path integrals over the paths in the configuration space. And for me, it would be useful to think about paths in the phase space. So phase space is syntactic manifold. In the simplest case, it would be just a convention multiple to the configuration space. And so I want to think of an integral over paths in the phase space, in the fact that we want to compute the trace geometrically corresponds to the fact that we integrate over the space of loops in the phase space. The paths which start and end at the same point. This is what trace does. And so this is an integral over the kind of a syntactic measure, kind of pointwise syntactic measure. So you have a so it's loop, it's just a collection of points. So for each point, you just use syntactic trivial measure on the phase space. Then you assume that maybe if you make more and more points, let's see the conversions of measures loop space, it will not, but no matter. The interesting part is this exponential factor, which is the so it has two parts, the real and imaginary. So the imaginary part only knows about the syntactic structure. If you had, so let's say locally, if your loop is small and it fits just one domain of Darboux atlas, then in this domain you can represent the syntactic form as dpdq, and then you take the inverse of that, let's say pdq, and that's what you integrate. Reduce the imaginary part of the space. Yes.
Your basic is necessarily
it just I said that well, Feynman was thinking about the configuration spaces and well, the phase spaces which are associated with configuration spaces and convention part. But idea is to generalize this formalism to or general syntactic manifolds is so the assumption of being convention bundles. So there is IPDQ term. I will remind you how it's defined. And then there is this, so it's an integral over the space of parameterized loops. So you need the parameterization in order to be able to write the second term. Second term is the following. You take so you have a loop, you take the pullback of the Hamiltonian function. So the operator H hat responds to some function on the phase space. Pull it back on the circle, and then you integrate below the instant measure ds, or S is parameter. Now I will make an assumption that my syntactic manifold is sufficiently analytic, so it can be complexified. Not always the case. Assuming it's a real slice of a complex syntactic manifold, and then the space of loops in this real syntactic manifold would be a real slice in the space of loops. So loops being ordinary loops, maps of the circle. But now loops into the complexified. And now this action is taken exponential. I view it as a holomorphic function on the space of loops valued in a complex complexity. Now, what is so we want to understand the critical points of that function, because those will give rise to Lefschetz thimbles. So the critical points are the one-periodic solutions of the Hamiltonian equations with complex So the variables being now complex variables P and Q, and the Hamiltonian multiplied by minus I beta. So this is a slight modification of the familiar Hamiltonian equations, where which you normally write for real variables and there are no factors of I. But here, just because of the nature of the problem, this factor of I is present, and it was overlooked by many people who work directly in the integration space. You might not see it so much. So the point is that even if you think of if you assume, let's say, that your variables Q, which are like coordinates of the integration space, are real, and you force the momentum, the P, become imaginary very soon because you have this I out of the utility of the Hamiltonian, and vice versa. So these trajectories do not fit in the real syntax manifold. They have to extend in the complexified. Now, this problem can be generalized if you have several Hamiltonians. So you can introduce several generating parameters that generalize temperatures. So the equations can be modified in some way. So let me make a further assumption, just to simplify the presentation, that after perform this complexification, and actually partial complexification, that my complex symplectic manifold, the homomorphic symplectic form, is actually an algebraic integrable system. So what it means is that it's a complex manifold with a homomorphic map to a domain complex vector space whose fibers are Lagrangian, and in fact they are principally polarized abelian varieties. So this is a one of the possible complexifications of the notion of a real integral system. So in real integral system, you have the structure of Liouville vibration with the fibers, if they're compact, being tori of dimension half dimension. When you complexify this whole picture, you have several options for how you complexify compact torus, and complexify it to make an algebraic torus, or you can complexify it to make an abelian variety. So this is the choice which I'm taking here. So the Lagrangian fibers are principally polarized abelian varieties, so the quotients of vector space by the largest whose rank is twice the dimension of the space, and so they depend the appearance of a new feature which is not seen in the real world, the appearance. Quite often, the examples with abelian variety is the Jacobian or Green variety of some curve. It becomes spectral curves. You know, operators and spectrums given by those curves. Not always, but almost.
But where is it not?
So there are examples of integral systems. Well, if you, I know many examples when you drop the condition that the polarization is principal, you can get it from the family of Calabi-Yauss. Family of Calabi-Yauss will give you right examples where your variety is a modular space of bundles, some elliptically fiber surface. You know, so, but most of the time you can find some curve, some family of curves which we don't. Now, so when you have the structure, you can use the complex analog of Arnold-Liouville theory and solve these equations in using just passing to the proper variables being the action angle variables. Now, what Arnold-Liouville didn't know, because they were real people, was that in the complex world, these angles have two types of periodicity. you have the periodicity in the period 2 pi, and then there is a double second periodicity with a period which is determined by the period matrix. Now, how you choose the normalization of your angles is actually ambiguous. There is an interesting bit of special, so the whole structure is called special Taylor geometry. It's one term. So the choice of this of action angle variables is not unique. Locally, you have the whole the action of the symplectic group of integer coefficients which act on those choices. So in particular, in my choice of the periodicity for the angles, I chose integers and then the period matrix. I could have chosen the inverse of the period matrix. So this is related to the fact that the differentials of the action variables, which are one differentials of the base vibration, they are obtained by pushing forward the symplectic form along one cycles of the fiber. But you have 2 R cycles of the fiber, and you only need R differentials of the base. So you have many choices. You need to choose Lagrangian sublattice. It's Lagrangian with respect to the intersection form, which you define using the localization. So close structure. So this is the multitude of action variables which I mentioned, which is important in what we're doing. So now suppose that we pass to the action variables. The solution of Hamilton equation is very simple. Action variables stay put, they don't evolve in time, and angle variables just evolve linearly in time with the angular velocity given by the derivatives of the Hamiltonians with respect to the action variables. So now we need to impose the condition that our trajectory is periodic in the period 1. So we need to close it. So that means that the angle being a multivariate function, its values of 0 and 1 differ by the periods, which are these integers or period matrix type integers. So that imposes a condition on the value of the action variables. So your angular velocity has to be exactly such that in time 1, you will perform exactly not one. You will precisely travel vector of the you will accomplish a vector of the lattice of periods. You don't know in advance which vector you will find around. But once you've done that, so you can see that the trajectory, the periodic trajectory, will just realize a one cycle in the fiber over some point of this. Now, so I said it's an NM cycle. In order to write it this way, you need to choose a basis. So a priori just one cycle. So genetically, you have a loop in your phase space, and the Hamilton equation is telling that this loop actually sits in the fiber of the Lagrangian vibration. Therefore, it must realize an element of the fundamental group of the fiber. That's all I'm saying. But I should say a little bit more, because the fact that this loop is a result of a linear flow on the invariant variety, whose velocity was determined by the derivatives of the Hamiltonians with respect to the action variables, can be summarized in the following nice neat statement. In fact, the point of the base, which corresponds to the fiber where the periodic trajectory is sitting, is the critical point of a new function, which is called the superpotential. The reasons which I told you is not much time to explain. And this function has 2 terms. So the second term is just a pullback of some function on the base, which was the original second terms. And the first term is defined only locally because it requires the choice of these integers and them. And so it's essentially this first term is a period of the and the derivative of the symplectic form along the one cycle of the fiber. So because of these choices, there's not as we pay for these choices. The payback is that the domain of this function is not the base of the integrable system. Explain what is domain and what's the definition of the function. So if you think about this Lagrangian vibrations, not all fibers are equal. Some of them are actually singular. You have the discriminant variety in the base where which characterize the fibers where some cycles have vanished. So in order to proceed, I need to pick a point, some generic point U0 in the base which corresponds to a non-singular fiber, and for every other point, I need to pick a homotopy classical path connecting that other point with the point U. So that way, so that defines a cover of the complement of the discriminant. It doesn't have to be a universal cover, but it's some cover of the universal cover, which parameterizes what? So it parameterizes the choices of the homotopy classical path connected by running point and the base point. And now, in addition, I need to pick up a cycle in the fiber over the marked point, and then using corresponding connection, I can transport the cycle over to the running point U. So as I transport it over the path, the cycle will sweep a two chain. So my superpotential is an integral of the holomorphic symplectic form over this two chain multiplied by I minus the function which is 2 vector. So my so the domain is the space of pairs. So it's a space of it's a fiber of this migration together with the choice of the cycle at this time. So it's a sub-quotient, it's a quotient of the universal cover of the complement of the base term discriminant by the subgroup which of the subgroup of the monogeny group which preserves this type. Because so this space has it is disconnected, it has connected components. The reason it has connected components is that it has cycles which are not primitive. Like monogeny may change one cycle to another cycle, but it doesn't change the fact that the cycle is primitive or not primitive. So at least one reason for the space to be disconnected is that you can have multiple ones. There's a component where the cycle is actually trivial, then it's just this function contains only the second part. So then we're just dealing, so this would correspond to the stationary points of the original component system. Some of these periodic loops could be actually constant loops. Now, this picture and this origin of this potential W, it's striking. Actually, it turns out that this story has a beautiful connection to four-dimensional gauge theory, both in physics. So in physics world, it would be systematic analysis theory. In mathematics world, this type of theories are used in defining invariance of four manifolds, Donaldson theory, Witten theory, Witten theory, all kinds of. So depending on the integral system you start with, we have a different way of getting four manifold invariance. So if you take that gadget and study it on a specific four manifold, which is a product of two-dimensional torus and a disk with and you work equivariantly with respect to the rotation of the disk, the equivariant parameter for the rotation of the disk turns out to be a non-constant H1. And so, and from that you can compute this function W superpotential by doing localization on this homogeneous spaces. So by doing some kind of covariant analysis of theories. So it's actually powerful, this relation is quite powerful. But now I wanted to tell you another story, which is so we're not finished yet. But mechanics, I just want to detour, reminisce about what I just
Just a very quick question. In this quantum mechanics machine, you have this assumption that it's an integrable system.
I made an assumption that it's an algebraic system. Yes.
Right? How realistic are the Lagrange or the
Okay. Depends what you call realistic. So anything so whatever we can say about nature, we usually we say by approximating by some tutor. Right? There is another extreme when people say that well, nature is maximally chaotic, and so that could also be an interesting starting point for this study. There's nothing wrong with that. It's just that here I have an interesting way of I have some tools which I can use to go further. But, the point is, of course, nature as we see it doesn't seem to be integrable, but it is integral to approximations. When I look at the motion of planets around the solar system, it is well approximated by Kepler's laws, right? Which I agree. But of course, there are corrections. Okay, so this story came approximately started when Lefschetz passed away. So approximately when this book, which I mentioned in the beginning, was published, physicists started meeting in a remote place in Sicily called Hitchin, on top of a volcano, to discuss the challenges of subatomic physics. And one of the textbooks which came out of those lectures was a book which I studied. It was by Sidney Common. And in this book, he would explain that to compute the boundary amplitude for the particle in the, let's say, in anharmonic oscillator potential, or which is saying to compute the approximate spectrum of the Schrödinger equation corresponding to the one does it by computing the approximating the path integral, where now this is the integral Feynman style, it's really in configuration space, and there is no I in the exponential, it's purely real quantity. And unlike the Euler-Lagrangian, which is the difference between the kinetic and potential energy, here in the exponential you see the sum of the kinetic and potential energy. This was justified by saying that, well, we wanted to study the evolution operator in the imaginary time, is the minus beta over h bar h hat without an I. That means that I'm moving in imaginary time. So I should, whenever I see a time in Lagrangian, I should put an I in front of it. So that will, since the kinetic energy is the velocity squared, if I put an I in front of the time, so time derivative also counts, the velocity squared will change the sign. So instead of this difference between the kinetic and potential energy, you get the sum, and the I, which you normally have in front of the whole action, disappears because they have dt. So that was the argument. Then Coleman say that now we want to just try to do this find solid points and the critical points of this pattern. And he would look for them with x being real variable, which is reasonable because well you have the real potential, real functional. You want to find these critical points. Why don't you look for them? Real. So this is the younger version of Stephen Coleman. Question because passed away. He passed away just before I understood the story, so I was going to tell you. Anyway, so Sidney said, okay, so you just extremize this functional because you have class in front of the potential, we have a plus in front of the force. So this is quite often represented as the motion in the inverted potential. And so people observed long ago that if the time this data was actually infinite, then the only solution which has finite value of the action is such that if your initial and final point are the same, let's say the right minimum of the potential, then the associated energy, and the energy now is defined unusually as a difference of kinetic energy. So then the only solution, is when the particle just stays. But if your initial condition is the right minimum of the potential and the final condition is left minimum of potential, then you have a neutrino solution with vanishing energy, and the solution is actually solves the first order equation, where this velocity is equal to negative square root of the twice the potential, which can also be written as the gradient of some function. Here starts the connection to Morse, because this is the gradient trajectory. So this function is actually polynomial. So for the anharmonic potential, U was a partial polynomial, and this K is a cubic polynomial. And this function you can write, I mean, the solution you can write explicitly. And so qualitatively, what it does is that it stays at the one point for a very, very long time. Then, in a short amount of time, omega inverse jumps from one minimum to another, and that stays put there the rest of the times. But it's not unique. So this is parameter T naught. So there is no obvious reason for the particle to decide to jump from one place to another, so it can be anywhere. So this is the modulus of the solution. So we just drew two pictures, two possible solutions. Now, as I said, everything happens, so this action happens in a relatively narrow period of time. Omega inverse, omega is related. So omega is related to the frequency of the classically allowed motion near the minimum of the potential. Just classically give a little knock to the particle, it starts oscillating back and forth, and the period of that motion will be 2 pi over omega. So now what to do next? Well, Colton said that I think he also called polygons, so maybe that okay, so you actually there are other types of configurations where particle actually swings back and forth from one minimum to another minimum, tunneling. Tunneling because this motion happens under the potential, under the classically allowed, under the barrier of the potential. So it's classically will not be possible, but it happens with dimensionally time. And so you have a kind of configuration, just take a sum of these functions and they will oscillate with the n modular. And so then there are some interesting plausible arguments which say that maybe error in implementation. So if you want to compute the matrix element for the particle to start at the right minimum and end up at the right minimum, you sum all the configurations when you have an even number of jumps. And if you want to study the transition amplitude from right to left, you sum over the jumps where you have an odd number of jumps. And so they contribute. So that is so distributions are roughly in terms of the expansion of the exponent. The reason being that so the exponential e to the minus n s naught over h bar is the action computed on this superposition of instantons and non-instantons. Most importantly, I was taught, so the most important factors are these factors beta to the n over n factorial, which are the volumes, the configuration spaces where it parameterize these positions of jumps. So this is how you accumulate an exponent which then translates to the fact that the Hamiltonian has two energy eigenstates.
The value.
Of the vacuum. So the point is that so you sum up, so you can realize this, these sums are just even and odd parts of the expansion of the exponent. So the fact that you have even and odd parts translates to the fact that hidden there are two eigenstates of the Hamiltonian with very tiny, very narrowly separated levels. So the plus and the minus, whose separation is exponential minus the actual instanton divided by h1. So, so this is the example, first example of a non-reducible effect. So if you try to compute it by doing h bar expansion, you will never see this term because this function on the right hand side has zero Taylor series. But it has to be there because the well, Feynman showed actually ground state of the Schrödinger operation cannot be roughly linear. So the hard truth is that I always had troubles with this discussion because the superpositions of instantons and anti-instantons, right, naively, they're not solutions. They're not the critical points of the action. Because as I start with, the only solutions to find in action of those equations are such that either have one instanton or no motion, let's say. Assuming that x was real. And so if you actually honestly try to expand your action and path integral around this configuration, you will get a term which is linear in the, so if you take a variation inside, and you expand, you have a term which is linear inside. And this is known in quantum field theory as a tadpole. So what it does, if you try to integrate over side, it will shift. And by keep the first and second order of expansion, you now try to do Gaussian integral over side. Practically, it will shift the original configuration by the amount proportional to the failure in configuration to solve equation of motion, the critical point of the action. So what it means is that you start with this crazy configuration of instantons and anti-instantons, you expand your action around it, and it tells you that it wants to push it into some direction in field space to be closer to the critical point. So begins the process of computing corrections to those configurations to compute the forces between instantons and anti-instantons, which is studied by many famous people. Instead of trying to find the honest solution first in expanding ground. But I suppose that if people had infinite computational capacity and they were honestly doing this procedure iteratively, so Anders Schwarz actually pointed out that this procedure of correcting solution is similar to the Newton's method of solving equations. If you want to find the root of some crazy function, you take any first guess, then you will draw a tangent to the graph of your function at this point. It will intersect the horizontal line at some point. That's your second approximation. Then you iterate. If the function is convex, it will converge. If not, then you're out. So instead, we show the systematic and proceed with finding the truth critical point and then spawning the Lefschetz thimbles. We actually already classified these points abstractly. Now I want to tell you something about more specific about this particular example, which is the example of next. How much time do we have? So the reason I made an assumption that my system is not a algebraic system is that this textbook example of the anharmonic oscillator is an algebraic integral system because the levels, so if you complexify the coordinate of momentum, take a level set of the complexified Hamiltonian, it is an elliptic curve. You have to partially compactify, so you have to add 2 points to make it a real elliptic curve. But that's the thing about all integrals, all algebraic integral systems. When they present it to you, the fibers of this regular vibration are typically non-confined, but there's a natural way of quantifying. So in this particular case, we can exhibit the structure of vibration. So the base of this vibration is characterized by the complex energy value of the integrable. And so there are 2 special points. The discriminant in this case consists of 3 points. So 0, infinity, it should be just 2 points. So 0 and this value of this squared over 8, which is the what you get if you set p and x equal to 0 in the formula of the Hamiltonian. This is where so I drew the little picture of the potential profile, and the blue line represents the energy level. So when the energy level corresponds to the local maximum of the potential, double well potential, so there is a local maximum of 0. So this is the elliptic curve develops in each direction when it's pinched at 1 point. Now, the interesting point, the most important point when the energy is equal to 0, and this is actually, so the elliptic curve which we are given actually is pinched at 2 points. But that's a feature of this image of the problem. So it is in general, so since my condition on E to sustain a periodic trajectory corresponding to some cycle in this fiber is expressed in terms of a period, so that in this case, the condition is simply that the differential, the x over p, which is the holomorphic differential of the beauty curve, multiplied by I, so its period along this cycle gamma, we don't know in advance which cycle it is equal to the specified number beta. So it's a kind of a terrain problem. I give you a period, you give me an elliptic curve. So it's a transcendental equation, of course. But we can say something about the solution of this equation when beta goes to infinity. That's the limit which is of most interest if you want to find the low energy angles. And in general, for the more general algebraic systems, when all Gibbs parameters beta k are set to infinity, the expectation is that you will actually approach the most singular part of the discriminant, maximum deterioration. If you just send one parameter to infinity, you will approach the generic stratum of the discriminant. As you send more and more parameters to infinity, you will go deeper and deeper. That's the expectation. It's not happening. But now, suppose we are in the generic, so suppose we don't tune all betas to infinity, just one. So we will approach maybe one stratum of the discriminant. In the example of anharmonic oscillator, when my base is one-dimensional, it is the general case. So there is a cycle which vanishes precisely at the stratum of discriminant. And so if I take the nearby fiber, so the point U which is nearby, which is a non-singular fiber, then the cycle is there. So there's this distinguished one cycle fiber, which will disappear at the singularity. So that 2 chain, which I was using earlier to construct my action functional, will actually have a close up into this case. And then the interesting story part is that so we need to not only the vanishing cycle, but the trajectory itself actually will not be following the vanishing cycle. It will be following some of the long cycles, which can only draw a piece of this picture because the zoomed in vanishing. And now the long cycle is not intrinsically defined. It's not defined intrinsically because if I go around with my discriminant and come back, the long cycle will pick up the contribution of the vanishing cycle. That's the Lefschetz formula. In some multiplicity. And so that means that in computing the period of whatever differential I want to integrate over my cycle, if I parameterize my base by the period along the vanishing cycle, so some local coordinate which should vanish the discriminant, then the associated period along the long cycle will have this characteristic in generic form, 0 Z, times some integer delta. And from that, so this is the kind of universal local behavior, and that allows me to make estimates for the locations of the points on the base, which correspond to the periodic trajectories, which correspond to the critical points of complexified action, which correspond to the Lefschetz thimbles. Going back to the example of anharmonic oscillator, so these instantons and anti-instantons, we can now understand better using the picture for all the solutions. So, but I need one more refinement maybe to look at. So, in general, we might have some symmetries which commute with Hamiltonians, which act on the complexified morphisms. And these symmetries are useful because I can refine my trace and refine the spectrum of the Hamiltonian by inserting the corresponding group element in the trace. And there are two cases, discrete symmetries and Lie group symmetries. I will talk about Lie group symmetries later. For the discrete group, the presence of the symmetries means that in addition to the integral over the loop space, we can also study and should study these integrals over the twisted loops, where the initial and final points are related by an element of the group. You only have to specify the conjugate class. And in the case of the anharmonic oscillator, the symmetry was Z2, just one symmetry which flip the sign of both X and P. And so we can compute so now we need to compute two traces. And now, instead of studying the twisted loops on the original trace space, twisted being by the reflection X equal to minus X minus P, I can model out my space by this two symmetry and produce an A1 surface, also symplectic, actually. We can blow up the singularity without description. So it would be a surface parameterized by coordinate capital P, capital X, and capital Y, related by the P X equals Y squared relation. And now my curve will become again an empty curve now sitting at a surface. So this is the cubic form of the empty curve. So this curve C tilde, it's a Z2 quotient of my original empty curve. Now, the critical points contributing to two traces will be periodic quantities on this smaller curve. And so, using this logarithmic asymptotics from Lefschetz theory, here quite explicitly one finds that the positions of the points where the trajectories close up and periodic, they form this pattern. So they are labeled by two numbers, two integers. One of these integers n is arbitrary, not zero. And it is well defined because it's defined as an intersection index of the cycle representing the trajectory with the vanishing cycle. The vanishing cycle is well defined, my trajectory is well defined, the intersection number is well defined. That's the number n. That number is the number of instantons, anti-instantons in the common. The second number was missed by the classics of the subject, and that's the contribution of the of the dimension cycle to my trajectory. So that contribution is defined not uniquely because of the monodromy. And so the second number assumes only 5 number of values, so to speak, given the first one. So that's the conical structure of the set of critical. We form something like a solar system. So we have a point of n equals 1, which is very close to the discriminant when n equals to infinity. And then you have 2 points when n equals to 2, and then 3 points when n equals to 3, and so on. But then we think an exponential decreases, but one should remember that this is done in limit rate is extremely large. So this is they're all very close to equals to 0. So this second number M essentially represents the fluctuations, the classically loud motions, which one can superimpose non-linearly with a boundary in order to produce an actual solution of okay, so let me stop here and I'll start with the continuous symmetries and the extension to the field theories. Second one.